at a very nice conference 2 years ago. This is a picture of the Iceland's conference, and in this group discussion, in particular, the arrangement of a camera crew and the microphone. And today, I'm going to talk about the emergence of a graviton from some kind of a quantum spin model. Because time, I will mainly talk about the background motivation, and maybe I just list the results. How should I advance this?
Spacebar.
Okay. So we know that our world is described by standard model and general relativity, where there are seven deep facts, I call them mysteries or wonders, was put in by hand into the theory. One is we have identical particle, we don't know where it's come from, and all interaction, gauge interaction, why, and who ordered the fermion, why the fermion mass is so much lighter than the Planck scale, why weak interaction only couple the right-hand fermion, where Lorentz emergence comes from, and where gravity comes from. And we like to unify all this, meaning that we wonder whether it is possible to obtain all these wonders from a single structure, instead of put all this property by hand into the theory. The problem is that everything has to come from something, so where should we start? Here we still do quantum physics, so therefore it's very natural to start with a qubit. That's the most basic fundamental building block of everything. So in this emergence approach, we think a qubit is a fundamental building block of everything. And so under this picture, the space is simply a collection of qubits. If there's no qubits, there's no space. And so if the qubits have certain dynamics, the ground state of those qubits will be corresponding empty state, empty space. And the excited states, excitation above the ground states, will be the like elementary particle in space. So this is a picture of the space which formed by qubits, which is black means m equal to 1, and white means m equal to 0. We can spin up, spin down, so if you use spin language. And so from this approach, we are no longer, to understand the origin of the elementary particle, for example, we don't care about the smaller building block. You know, the science is driven by the reductionism. It's driven by the belief that to gain a deeper understanding, we need to get smaller or more basic structure. And however, in this approach, the building block is trivial, it's a qubit, so we already know what is building block and everything. We don't need to looking for them, it's known. What is non-trivial, actually, is how those building blocks, how those qubits are organized. So the picture is that the organization or order of the qubits actually is the origin of everything. So its origin is not from something, but from a structure, from the order, from organization is the origin of everything. And this is really where kinetic matter comes into play, because in kinetic matter physics, a standard topic is to study how quantum spin organized, which occurs on different phases of matter. You know, that's a study of order. And actually, there is a very general theory for phase of order, which is Landau signature breaking theory. For a long time, we believe that all possible organization of a degree freedom is described or characterized by Landau signature breaking theory. A standard picture is that like this anti-fermionic spin is up and down, and that's the ground states, and then the variation of this order, or distortion order, give us spin wave, and which is like a collecting mode on excitation. And but however, the trouble is that with this picture, we never get a gauge boson, we never get a fermion from this picture. So it looks like it's hard to understand how photon and the fermion emerge. But now here the quantum innovation comes into play, because these anti-fermionic states, from quantum information point of view, is trivial. It's a direct product state. It's a local direct product state. And nobody cares about this state in quantum information. And unfortunately, condensed matter, we think this is our universe for the last 50 years. Certainly, there are more complicated states, which are more highly entangled. So therefore, and this represents a new state of matter. Actually, a new state of matter do exist. They are described by quantum states with a long-range entanglement. And one example of a long-range entanglement is so-called the stringnet states. The stringnet states is simply formed by two steps. One is that we view a state where all spin is pointing down is a no string state. The loop of up spin is a string. Then the superposition, all kind of a loop, like equal with the superposition, all kind of loop, it's a particular quantum state we call stringnet condensed states. So this state is very different from these Dirac states. It has a long-range entanglement. And this long-range entanglement actually is the key to gain a new understanding of a many qubit system. And in particular, if we believe our space is a stringnet liquid, then actually we can understand 4 of the 7 wonders. So we have identical particle, and we can have a photon or gluon, and the Fermi statistics can arise. Okay, gauge boson actually is a fluctuation, like density fluctuation of string. So density wave is a gauge field actually in the string liquid. And the end of string gives us a gauge charge which can have Fermi statistics. So the key is that so this long-range entanglement, more particular in this stringnet picture, gives us unification between gauge interaction and the Fermi statistics. So the next question is that can we unify one more things? So here we unify 4 wonders. So let's do one more, 5. Can we do 5? So this is a recent work I just posted a few days ago. That we studied 2 quantum qubits model where the graviton may emerge. Now here we will emphasize that we have a strict definition of graviton. The graviton not only is a helicity plus minus 2 mode, but they appear as the only gapless excitation in the system. There's no other gapless excitation. And there are 2 qubits model have this property that the graviton emerge at low energy. The first model we call L-type model. The Hamiltonian is there. I just too complicated to write. I won't write here. But it has this very strange cubic dispersion relation. This result is very reliable. And it's a cubic dispersion relation because the linearized graviton, or linearized effective Lagrangian, have this local gauge invariant. Means the Lagrangian density is gauge invariant. Okay, just. The next model is N-type. It has a property that only action is gauge invariant. And this one have a linear dispersion relation, but we don't have a reliable handle for this model. So, so this basically to emphasize that this long-range entanglement seems is very important. The fluctuation entanglement may give us graviton as well, in addition to gauge field.